Welcome to section 6.8, our final section for the semester. We're going to be looking at exponential models, specifically the growth and decay model, exponential growth and decay. And it looks like this. It's a variation on our exponential model that we looked at in 6.3. And it's used as specifically for exponential growth and decay. So if it says it obeys the law of uninhibited growth, or if it's exponential growth or decay, it's going to follow this model. All right, so what does this mean? Well, a of t, this is function notation, okay? So it's not a times t, it's a of t. This is our amount at time t. Okay, so our amount at time t. So this amount is going to change depending on what time we're looking at. So we're looking at 4 hours, 5 days, 3 years. That amount is going to change. This a with a little zero, we call that a naught. A naught is our initial amount. So that's going to be our starting amount for any given problem, and that's not going to change. Once you figure out your initial amount, it's going to stay the same throughout the entire problem. The k and the t, that's our exponential part. The k is called our growth or decay rate. Growth or decay rate. And if k is, you don't have to memorize this, but it just works out this way. If k is positive, then we have growth. Oh, I keep putting an a there. Growth. And if k is negative, we have decay. So our numbers are going to get smaller, which makes sense. You got a positive exponent, it's going to get bigger. If you have a negative exponent, it's going to get smaller. Okay, so that's our k is our rate. And then t, of course, is time. Okay, so we have our amount at time t. Remember, that's function notation, not a times t. That's a of t, amount at time t. We've got our initial amount, we've got our growth or decay rate, and we've got our time. So those are the 4 key pieces that we're looking for here. Now, this same exact function can be written as n of t if we're looking at a number of things instead of an amount. So it could be n of t equals n naught e to the kt. It's the exact same formula, just a different letter. And sometimes you may see it as p of t for population. And we'd have p naught equals e to the kt. So this letter is interchangeable, a and p. Those are all the same equation, just whether you're talking about an amount like grams or a number like number of things, or p like a population of humans or animals. Okay, so now that we know what the formula looks like, let's go ahead and erase this. And we can look at this example that we've got right here. Okay, so I'm going to put our formula back up here so we have it. I'm going to use it in the version of a, but remember it can be any letter. So we've got a naught e to the kt. Okay, so this is an example problem. We have a bacteria population. We know that it's modeled by this equation, so we're using n this time, where t is the time in days. And we want to try to answer these questions. So let's start with part A. What is the population at t equals 0? Okay, so if you look at this equation, this is a standard form. We're given these two numbers. We don't know the amount at time t, the number at time t, and we don't know the time. And that's pretty typical when you get your setup done. We're either looking for a number or a time. So you've just got to figure out in each question, are we looking for the number or are we looking for the time? So this one, what is the population at t equals 0? There's 2 different ways that you can look at this. Okay, you can say, well, I know the time. I can plug the time in. Let's do that. So we've got a of 0, okay, our amount at time 0, is equal to, let's back up there. Let's use n because that's what our problem is. Okay, so we've got n of 0, our number at time 0, is equal to 850 e to the 0.09 times 0. Okay, so you can plug that into your calculator, or you can remember that e to the 0, anything to the 0 is just 1. That whole thing cancels out. We've got 850 times 1 is just 850. So we get the number of bacteria at 0 is 850. Okay, so you can plug t equals 0 in and you get that. Or you can remember that the number in front is our initial amount. And you could just read that right off of here is 850 and you get the same answer. And that's why when you plug 0 in here, that whole thing's always going to be 1 and you just get the number out front. Okay, so you can either plug it in Or you can just remember to use the number up front, and you get 850 for your population at time 0 or your initial amount. Okay, that's what initial amount means. All right, so there's our initial amount. Okay, so let's move on to part B. What is the population after 4 days? 4 days. So are we given a time or an amount? That's got to be a time. So we've got t equals 4. And so just like we did up above, we're going to plug 4 in here. So our number at 4, n of 4, we're going to plug 4 in here. We've got 850 times e to the 0.09 times 4. We're going to put that in our calculator. Now when you put this in, it's probably going to look like 850 times, you've got to find that E button. It's the shift of the LN button. And it's if you have one calculator, it's going to pop up a thing like this, and that's your exponent. If you have the other calculator, it's going to pop up a little box right here, and you're going to type in the exponent. Okay, so one way or another, if you have the little box, it's going to look exactly like this. If you have it like this, then you're going to put it in like that. Okay, so it's going to look like one of these. And when you plug that in, you're going to get, you should get 1218.33 if we round that. Okay, so put that in our calculator, we get 1218.33, and it keeps going. Now, when you look at the answers in the back of the book, a lot of times we're talking about a bacteria population, so we're talking about living things. And we don't usually like to talk about parts of living things. We wouldn't want 0.3 of a bacteria. That's a third of a bacteria. That wouldn't be a good thing. So usually when we talk about living things, we go ahead and round it to the nearest whole number. So we would go ahead and say 1218 bacteria. Okay, I'm not too picky on that, but when it's multiple choice or comparing to the back of the book, you will see it rounded to the nearest whole number, and that's why. Okay, last one for this problem, part C. When will the population reach 5,000? Okay, so is this a time or an amount? This is an amount. So this is the number that we're looking for here. So this is n. Okay, so this time we're going to put this in for n, and we're looking for t. So we put this in for n. We get 5,000 equals 850 e to the 0.09t. Okay, now in these two cases when we're putting in time, it's just a matter of putting it in the calculator. But here, when we get the amount, we're going to have to solve this because we've got t up in an exponential. But we know how to do this. We did this in the last section. We know that we need to get the exponential alone, and then we're going to take a logarithm to get that t out of the exponent. So first, let's get the exponential alone. So we're going to divide by 850. Okay, I'm going to come over to the side a little bit here so we don't have to erase all this. Okay, so we're going to have, coming this way, we're going to have 5,000 over 850 equals e to the 0.09 t. Okay, and remember from the last section, we've got an exponential. We need to get this down. So what do? We take a logarithm, right? So if we take a natural log on both sides, we've got natural log of 5,000 over 850. That's just a number. You can put that in our calculator. On the right-hand side, we have natural log of e to the 0.09t. Now, we don't even have to bring that down because remember, natural log and e, they cancel out. So we get natural log of 5,000 over 850 equals 0.09t. And now we can solve for t. Divide by 0.09. Divide by 0.09. Put this in your calculator very carefully. It should look just like this. Natural log, make sure the parentheses go around the 5,000 over 850. N parentheses, and then over 0.09. And you should get 19.69 if we round. 19.69, and our time is in days. So this is in days. Okay, so 19.69, and our time is in days. All right, so going back and looking at this, make sure that this makes sense. Okay, we start with a population of 850. After 4 days, we have, here, I'll box these off. We start with an initial population of 850. After 4 days, we have, we can box either of these, 1218. And after 19 days, almost 20 days, we've got 5,000. So that all makes sense. Our population is getting bigger. 850, 1218, 5,000. Okay, the numbers should make sense. Our population should either be getting bigger or getting smaller, depending on the problem.